Hello, in this segment, I will introduce you to the Hill cipher, which is one of the classical ciphers invented back in 1929 by a fellow named Hill. The idea of Hill cipher is pretty novel. It uses concepts from linear algebra. So let me directly explain the encryption and decryption process. So the encryption goes as follows. Suppose you would like to encrypt a message. What you would need is an encryption key. In the Hill cipher, the encryption key is a matrix. So you would need a matrix. Let me explain the dimensions of a matrix in a moment, but you would need a matrix. So here is your message. Okay, let's say a message is made of characters M1, M2, for a moment, M3. Okay, in that case, this is a 1 by 3 vector, right? Meaning 1 row, 3 columns. So you would need a 3 by 3 key matrix. So let me call the key matrix as K11. You will fill up the rest easily. Here's K3133. So you have a 3 by 3 matrix as the key matrix. All right. So what we are going to do is we're taking this matrix multiplication. So you multiply the message. This is the message, right? Message, and this is our key. So we multiply these two things. Let me explain what is the reason for multiplying the matrix message and a key matrix. When you multiply matrices, things get mixed up very nicely. So you will be taking M1, multiplying with K11. M2, you will be multiplying with K21. M3, K31, you will add them. So that will give you the first ciphertext character. Similarly, you will take M1 multiplied with K12, M2, K22, M3, K32. That will give you the second ciphertext character, then the third. As you can see, now the ciphertext character C1, if I wanted to show you a graph, C1 depends on M1 as well as M2 as well as M3. That's very nice. That's kind of diffusion you would like to have. So the idea of diffusion is kind of explained in this Hill cipher under the hood, right? So diffusion is an important cryptographic property. When you're doing symmetric key cryptographic system, you want your messages to be mixed. So when you're re-encrypting, say, another message with only one character modified, you will not see that easily because you're now mixing up all of the message characters. Okay. Similarly, C2 also depends on M1, M2, M3. C3 also depends on M1, M2, M3. That's really nice idea of the Hill cipher. So, okay. So this is the encryption process. We explained the encryption. What about the decryption? The decryption will do exactly the same. You can use the same matrix multiplication, but you will need an inverse because we want to recover the message, right? So what we need to do is we need to get rid of this matrix. So all we have to do is take this ciphertext C. Let me call this as a ciphertext C, right? And the key vector, the key matrix is K, right? And the message is M for a moment. So what I'm going to do is extremely simple now. I'll take C, right? And I multiply it by K inverse. What will happen now? We know how C is obtained, right? C is nothing but M times K. So when I multiply it by C times K inverse, the K and the K inverse will cancel out to give you an identity matrix, which will be nothing. In the end, you will get M. So you need multiplication, you need inverse matrix multiplication and matrix inverse. You can implement encryption and decryption easily. So like the way I just did it. Encryption is take your message. You need to make sure the message length is a multiple of the number of columns. It has to match. Otherwise, you can't do multiplication of a matrix with the vector, right? So you need, for example, the message, say your message length is 9. You will encrypt the first 3 characters like this. And then you'll repeat the next 3 and next 3 times you will be repeating. Okay, but you'll fix the same key. Okay, that's the idea. The Hill cipher is actually not secure. It's broken. I will explain how to break it later. But the idea of diffusion is very novel in the Hill cipher. Even AES uses this concept. It multiplies 2 matrices to mix up things under the hood, and that idea was actually coming at least back from 1929. We can trace back. Hill cipher has that idea. There may be more before that, but that's not my scope this talk. Okay, so to summarize, this is basically matrix multiplication and inverse. Okay, there's one more caveat you need to be aware of. We make assumption here the message characters are alphabets, for example, English alphabets. So you'll be doing mod 26 because there are 26 English alphabet characters. Other than that, it's just standard regular matrix operations. Okay, so let me now show you a quick demo of a Python implementation of this idea. Encryption, as I said, is just taking your message and multiplying it with the key matrix, right? And the N here stands for the modulus I mentioned, 26 in the case of English alphabets. And decryption takes your key, invert the key matrix, and then multiplies the ciphertext with the key matrix. That's all. Okay, I have implemented my own matrix operations just for experiment purpose. You need matrix inverse, matrix join matrix, and matrix determinant, and all those matrix algebra related things that I am not explaining in this talk. But these are all standard matrix linear algebra concepts. You may want to consult if you're not familiar with these basics. That's not a problem. There are lots of other interesting materials online that you could leverage. All right, so let me now go to the main function and execute one for you. Okay, so the main function, I'm going to encrypt the message called crypto, right? Using my, as you can see, there are 6 characters here, right? So I'm going to encrypt CRY first and then PTO next, using this particular key K. Okay, it's a 3x3 key. So let me run it quickly. Okay, the message is crypto. It gets decrypted into crypto at the end here. Of course, the encryption is some gibberish that you see here. Okay, so let me now walk you through the encryption process. What I did, I converted the message into numbers, like C becomes 2 because A is 0, B is 1, C is 2, and so on. So I first encode the string into numbers, right? And then I get my row vector, right? That's basically what this encryption string is doing. It takes the key and the message string. As you can see here, it encodes the message string into numbers, right? We can print it for you if you wanted to see it. Message numbers, right? And then it encrypts that using the encryption algorithm. As I said here, for example, CRY is first these 3, and then the next iteration it encrypts PTO. Okay, this is basically it. And the encryption algorithm will give you back some number, and I also convert it back to string using the decode, which basically maps 0 to A, 1 to B, and so on. We talked about it in the Cipher, so I'm not going to explain the encoding decoding process. All right, that's all. So all you have to do is just use the matrix multiplication inverse for this Hill cipher. As I mentioned earlier, the Hill cipher benefit is that it mixes up all the characters of the plaintext. That's a really nice property called diffusion. Okay, just to warn you that this is not a secure cipher. The underlying matrix multiplication operation is a pretty novel one, though I wanted to highlight that. Okay, if you wanted to implement on your own just to play with these things, you may want to use something like NumPy from Python. However, you need to implement your own matrix operations like determinant, inverse, and so on, because it doesn't have modular reduction built inside, as far as I know. Okay, that's all. Thank you very much for your attention.